Hello everyone and welcome to this session in which we will consider a geothermal supply of heat and how to extract that, and we will make use of a computer to find out the work output and what the mass fluxes we need to have those work outputs. So what happens is you have hot water. So the geothermal energy, how it is utilized is you have water in the subsurface at a higher temperature, and then you extract that water to the surface. That water is usually hotter and it's at a higher pressure. Okay, so that high pressure, high temperature water is first flashed. So the meaning of flashing is it's converted into a two-phase zone in which you separate out the liquid and you separate out the vapor. In a two-phase zone, inside the two-phase dome, if you are flashing something, then you extract the liquid here and you extract the vapor over here. You come at this point and then you flash it. Okay, so this is called as flashing. So you extract the liquid and vapor separately, and then the vapor you pass on to a turbine. The turbine then rotates and you extract some useful work. So let's see what we have. We have high pressure water at 1.5 megapascal. So state 1, 1.5 megapascal of water and 180 degrees Celsius. It is throttled into a flash chamber which forms liquid and vapor at a lower pressure of 400 kilopascal. So state 2 would be at 400 kilopascal, x equal to 1, because like I showed, this vapor output is extracted here. This pressure is 400 kPa, but this is not extracted, this is extracted. Okay, whatever comes here is extracted. Okay, so let's call this as state E. So that is the exit state. So exit state is 400 kPa, x equal to 0. The liquid is discarded. Okay, this liquid is discarded. While the saturated vapor feeds the turbine and exits. So the exit of the turbine, so state 3 is at 10 kilopascal and x equal to 0.9. So essentially, once you have flashed to this point, you then expand it in a turbine and you go to this. So you essentially decrease the quality. Here the quality was 1 and here the quality is 0.9. The turbine should produce 1 megawatt. Okay, so the whole control volume, this control volume should produce 1 kilowatt, 1 megawatt rather, the 1000 kilowatt. So we must find out the mass flow rate of geothermal water in kg per hour. So we must find out the mass flux. Okay, so how do we go about doing this problem? So we can do this in multiple ways, but let's start off. Let's see how we progress. So m dot 1 is the mass flux inlet, okay, at the inlet. So let us write down a control mass, the control volume as the flash chamber. So for the flash chamber, the mass balance is m dot 1 is equal to m dot 2 plus m dot exit. This is the mass balance for this particular control volume, the flash evaporator. And m dot 1 H1 is equal to m dot 2 H2 plus m dot E He. How can we write this? This is the energy balance for the flash chamber. The flash chamber does not have any moving object, so there is no work extraction. Moreover, a flash chamber may be assumed to be insulated, so there can be no heat transfer as well. Okay. So here the unknowns are, everything is here unknown. Okay. But okay, so are the states known? Yes, H1 is known, H2 is also known, H exit is also known. So in this equations, in these two equations, we have three unknowns. Those unknowns are m dot 1, m dot 2 and m dot E. So these are the three unknowns. So what should be the fourth equation, the third equation? We have only two equations, 1 and 2. So what should be the third equation? So look, if we now draw this as the control volume, so this was the CV1 with which we could write equations 1 and 2, and in CV2, let's write down what the mass balance is. Look, the mass balance in CV2 is obvious. Whatever mass is coming in through point 2 is the same mass exiting at point 3. So mass balance is simple, m dot 2 is equal to m dot 3. So we need not write this. The only variable here is m dot 2. So then let us write down the first law of thermodynamics for the control volume. So the first law says m dot 2 H2 is the inlet plus q dot. So these are the inlet energies, influx energies. This is equal to the work output plus the enthalpy at the exit. Why have I written this as m dot 2? Because we have just seen that m dot 3 is also equal to m dot 2. So I have substituted this over here. Now a turbine, unless specified, is considered to be an adiabatic object. Okay. The process is so fast, there is not enough time for heat to be transferred. So then, and also implicit in this is that H2 total is equal to H2 and H3 total is equal to H3. Ideally, these should be total quantities, but we can neglect the velocities. We can neglect the half V square and Gz contributions from the total enthalpy, and we can simply write it in terms of the enthalpy. We don't need to account for all the terms. We don't need to account for the kinetic energy and potential energy. So this term goes away and W dot remains. So m dot 2 H2 minus H3 is equal to W dot, and in this particular equation W dot is known, H2 and H3 are also known, and so in this equation the only unknown is m dot 2. So thus we have three equations and three unknowns, and we should be able to find the solution. Let's go to our computer and solve. Md1 is equal to Md2 plus Me. First equation, m dot 1 times H1 equal to m dot 2 times H2 plus m dot E times He. M dot 2 times H2 minus H3 is equal to W dot. So W dot is the work done by the system, which is 1000 kilowatt. So W dot equal to 1000. H1 equal to, we find out from these states what the enthalpies are. Enthalpy of steam at P equal to 1500 kPa and T equal to 180 degrees Celsius. H2 is at enthalpy of steam at P equal to 400 and X equal to 1. This is the extracted steam from the flash chamber. Okay. What is the H exit? That is the enthalpy of steam, P equal to 400 but X equal to 0. That is the extracted liquid from the flash chamber. And correspondingly, H3 is the enthalpy at the exit of the turbine. At the exhaust of the turbine, we have a pressure of 10 kPa, X equal to 0.9. So, this is what we have. Okay. Oops, so there is a small error. So, this should have been m dot e. So, the software told us that either there are more variables or less equations, and that clearly meant I have named a variable wrong. These are small errors that creep in. So, anyway, we are able to solve the problem and the final solution. So, the required mass of geothermal water is m dot 1, which is 34.18 kg per second. So, that is how we tackle this problem. We break down the problem into different control volumes and see how it pans out. Okay. So, I hope you will try to solve more problems of this kind with the help of a computer. And these kind of problems look slightly difficult, but it is not really difficult. The reason, you just solve it part by part, and the essence of physics remains always the same. It is a conservation of mass, conservation of energy, and we have to make sure none of these are violated. As long as none of these are violated, you get the correct answer. So, with this, we conclude the problems for the first law of thermodynamics for open systems, and maybe we will do some more problems later on. And with this, I take leave and I will see you next time. Bye bye.